Welcome to the Science College Readiness Program. The goal of this program is to help you get better at your science skills as determined by what's important from the ACT at least. And the ACT science consists of three main areas: interpretation of data, your ability to read and analyze a scientific investigation, and your ability to evaluate models, inferences, and experimental results. Essentially look at an experiment that was done and make sense of it. The ACT science does not test how much science knowledge you have acquired. It tests your ability to think scientifically and take scientific information and make some sense of it. We're going to spend 18 weeks in this course. You're going to be here once a week, and we're going to take each of those three main topics from the previous slide and break them up into about 6 weeks of getting you really good at those skills, which will not only help you, of course, in the ACT, but it'll make you better in the science classroom as well in terms of your ability to perform a lab, understand a lab, make sense of a lab, explain a lab, which is where a lot of your knowledge then will come from in the science class. So we're going to start the first 6 weeks looking at the interpretation of data. And most of your questions on the ACT come from this type of an area. Also, a lot of what you will do in class, of course, also is interpreting the data that you either get or are given and making some sense of it. Specifically with interpretation of data, we're looking at those bullet points there that are listed, but we're looking at how one part of an experiment affects another part of an experiment, usually represented in a table or a graph or a combination of those two. So a lot of what we're going to be doing here over the next few weeks is looking at tables and graphs and the relationships between them and how to make sense of what's happening as an experiment is run. So let's just start with some real basics for graphing. Every graph is going to have a title. Generally that title is on top of the graph, and usually the way that is written, it will be the y-axis variable versus the x-axis variable. And more about that as we get going here. Typically on a graph, you will just, in a science graph at least, typically you will have just the quadrant here where you have both positives. You may get into some negatives in some areas, but for the most part you'll have starting at 0 or a small number, a low number, and working your way higher as you move left to right on the x-axis and bottom to the top on the y-axis. So a point like this red one here would have a relatively low x-axis value and a relatively low y-axis value in comparison to this blue dot here, which would have a much higher x-axis and a much higher y-axis value. So the basics of graphing. A lot of times in science classes, you will hear terms about the different kinds of variables that you're looking at. Those two main terms are the dependent variable. The dependent variable goes on the y-axis. Notice how it makes a little d out of that. And the independent variable goes on the x-axis. So you can make the top of your eye from that. What that means is this: the dependent variable, what's on your y variable, is actually what we're looking at in the experiment. It's what we care about in the experiment. It's what we're looking at, how does it change as the experiment goes on. So if you're looking at something like the motion of an object, you'd be looking at how the distance changes with time. So we care about the distance changing. That's the dependent variable. In biology class this year, you'll be looking at populations and how populations vary as time goes on or as different environmental changes occur. What we'll care about is the population changes. That would be your dependent variable. The time or the environment, that would be the independent variable. Another way to think about it is the independent variable is something that we don't control. It just happens. Time moves on. Environmental changes occur with us impacting them. So the independent variable is what we're measuring against. We're going to run something for a certain amount of time. We're going to let something occur, a number of occurrences, whatever that is, that's the independent variable. But you can remember, again, from the little trick of the y-axis, the vertical axis makes the up and down line of the D, and then the x-axis, the horizontal axis, makes the top of the I. So there's your dependent and independent variable. There are two main types of relationships. There are others on graphs, but the main two types that you'll need to know about are direct and inverse. A direct relationship is where both variables increase. So that'll look like this on a graph, where as the x-axis is increasing, so is the y. So if I look at a higher point here on my axis, I look at a higher point on my y-axis. Same thing, as I keep moving down, I keep having increases in both of those two areas. Or if I look at a higher y value, again I have a higher x value that would correspond to that. So that is a direct relationship. Both of those two objects go up. Another thing to consider is where the graph starts. And that would be, in math class, we'd call that the y-intercept. This would be your beginning value. So at the beginning of, if this were a time, at the beginning of time, we had 2 of whatever it is we were trying to measure, and then it increased from there. So this would be our initial value of the experiment. So direct relationship, both are going up. Inverse relationship then typically looks something like this, moving down and increasing with time or whatever is occurring. So here, as we look at this x-axis value, we have a y-axis value of 5. Now as our x-axis value has increased, our y-axis value has decreased, and this continues to happen. As we move across our graph, as the x-axis variable is increasing, the y-axis variable is decreasing. Or, another way to look at it, again, as the y value is decreasing, the x value is increasing. So 2 different ways to look at it, but this is an inverse relationship. So those are the 2 main types of relationships you need to know. Are they both increasing, or is one increasing while the other is decreasing? And that will tell you some important information as you get into a graph. So this graph here comes from an actual ACT question, and it shows you a couple of different things in terms of graphs changing over time. So one thing to look at here is what we're looking at is the age of a tree stand in years. So we're looking at years going on. We start down here at 0 years and we go to 200 years. So we're looking at over 200 years. Then how does the number of trees in a certain amount of area change over the time? We have 2 different graphs. Sometimes there will be a legend, which will be a little box that tells you what the dotted lines or straight lines mean. Other times it'll be represented right there on the graph, or there'll be a combination of those 2. So the pine, we see, has an initial value here of around 27,000, and then is following this path here. The oak, which I'll do in red, starts here basically with 0, and then increases some, and then decreases down to 0, and then increases all the way back up. It continues to increase and increase and increase. So what we're seeing is that the pine tree has what we would look at as an inverse relationship. We start with a higher value, and then as the x-axis increases, the y-axis decreases. So something is happening in this environment where the amount of pine trees that we have is decreasing as time goes on. Questions that could be asked about this would be questions of why. What is happening in the environment? Is it because as more oak trees come in, the pine trees get overcrowded? Could there be an insect or a plant that is coming in and infecting the pine trees, and so they're dying out? What would be the situation that would be causing that? So these would be some things to consider. Questions would be, as time moves on, as the years of time move on, what is happening to the pine tree population? Other questions that could be asked would be this. At what age were there 10,000 pine trees? Well, so you would look at 10,000 pine trees and come down here, and you can estimate on the graph that that would be somewhere around 50 years. Other questions that could be asked is, based on the trend of the graph, what would you expect to be the population of the pine trees at, say, 250 years? Well, just kind of continue that line and you'll see that it's getting closer and closer and closer to 0. So we'd probably say that there would be 0 pine trees, or very close to 0 pine trees at 250 years. Now let's take a look at the oak tree, because the oak tree gives us a very different situation. With the oak tree, what we have in red here, what we see is that we increase initially our population. So we start from 0, and now this is increasing. So a question could be, from what ages did we see an increase in oak trees? Well, from about 15 years to about 34 years, we definitely saw an increase in pine trees. Then something happened which caused the oak trees to decrease in population from about 34 years to 75 years. You'll also see that the pine trees had a decrease in that population there too, pretty significant decrease. So again, questions could be, at what point in time were both populations of trees decreasing? You'd want to look for where both of them have a decrease in Y value as the X value is increasing. Then, for whatever reason, the oak trees had a direct relationship. As time went on, the amount of oak trees increased significantly. So now we're looking at, again, an increase, a direct relationship between the number of trees and the age of the stand, the set of trees that we're looking at. One last question that is typically asked is, at what point in time did the amount of oak trees equal the amount of pine trees? Anytime you're looking at a graph and it asks you for when two values are the same, you want to look for a point of intersection. So we'd be looking at a point right about at 100 years where we had the same number of trees. And coming over here, it would be somewhere around 4,000, 4,500 trees. So again, you're estimating different values. One last thing to look at, again, a question could be something like, what would be the approximate number of trees of the oak trees at 250 years? So again, just continue that trend out. And so as we reach 250 years, we're looking at about 30,000 trees. We're looking at extrapolating a graph when we're going outside of it, that's what we just did, or interpolating a graph, looking inside the graph when we're looking at something like when did they have the same value. Here's one more graph, and we're going to start asking you some questions and get you working on some of these graphs here in just a minute. But this is another typical ACT graph, and what oftentimes makes them challenging is because of the fact that you have multiple lines on the graph. So what you always need to look at is what's on the axis and what are the units, because a lot of times the questions will ask you something about the units, and just looking at the units can help you figure out what's going on with the graph. You want to make sure you pay attention to the key, because then the key will tell you which line to look at, because the question will ask you something about what happened to the granite, the thermal conductivity. In this case, that's what's on the y-axis. You don't need to know what that word means, you just have to see, okay, thermal conductivity. What happened to the thermal conductivity of granite as the temperature increased? So I look over here and I see granite is the graph that has a solid line and then two dashed lines and then a solid line again. So that must be this one here. Right away I can get rid of all of the other noise, the other graphs on there, because I only care about the granite. But I need to make sure I pay attention to the key first. Then I can see that the granite had an inverse relationship with temperature. I had a higher value when it started than when it ended, and as time went on, or as the temperature increased rather, the thermal conductivity decreased. Another thing to consider on this graph would be a question of which type of rock showed an increase in thermal conductivity or had a direct relationship as temperature increased. Well, there's only one graph on here that is increasing. There's only one direct relationship, and that's this one down here. The solid line started at about 1.2 and we're up to about 1.5 as the temperature increased. So come back up to the key, basalt would be the only graph that showed an increase in time. Other questions that were asked or could be asked about this is which graph showed the greatest decrease in thermal conductivity as the temperature increased? Well, as I look at these graphs, this graph here started at a little over 6 and went way down here to just a little bit over 2. This graph went from 3 to 2. This graph went from 2 to 1.3, 1.4, and this graph increased. So for sure we know basalt is out. And then which graph had the biggest change? Well, that would be this one here. And looking at the dashed lines, that would be the rock salt. So these are all ideas and concepts you should be able to get just simply by looking at a graph without knowing anything about the actual concept. Ideally in science you learn the concept and the graphs as well, but right now we're focused on just your ability to interpret a graph. So now we're going to give you some questions to answer, see if you picked up on some of the topics from today. We'll come back next week and we'll get a little further into depth. The third week then we will actually give you some ACT passages to start to try to figure out.